Jimmy Buffett's confused about a lot of things, dark energy being one of them. But today we'll try to understand a bit about dark energy and the cosmological constant and how we infer its presence. So logistics, problem set number 11, due next Wednesday. We'll assign it on BSpace sometime today. Sections will be as normal this week, so Friday, Monday, and then the following sections will be your last sections Friday, and then I guess that's May 2nd, that Monday. And those are optional from the perspective of your participation grade. We won't be introducing anything new per se there, but I certainly would encourage you to attend if you can. If you're going to be out of town that following week, you feel free to go to the one on Friday. There's no lick trip, unfortunately. We weren't able to get a scheduled time before the final, so everything was going to be in late May, and we decided not to do it. Colloquium today at 4 p.m. in 1 LeConte is by somebody named Matthew Bales, who's from Australia. He's the director of a supercomputer center there, and he works on pulsars. It's going to be an interesting talk. I don't think it'll have tremendous amount of science in it. He's already given a lot of science talks on campus over the last couple of months because he's been on sabbatical here. But he will be showing lots of movies because he likes visualization of astronomy stuff. So it might be interesting for you to come. I don't know. There may even be a 3D movie. We'll see. Let's see. So the big news, well, it's not news. This is a big set of letters that I put together that would be of interest to you, and numbers too, with my Josh Bloom font. It's 3106 Echeverry is the final. 8 a.m. to 11 a.m. on May 12th, Thursday. I guess that's 3 weeks from now. And what we've decided to do with the GSIs is have a 2-hour review session during what would have been class time on May 5th. We'll very likely do it in this room, but there's a chance we'll do it in Evans 264. If that's the case, then we'll let you know, obviously, by BSpace. We should know that answer even by next week. So that gives you, sort of a week to prepare for the review. It'll give you then another week to work on your preparations for the final. And what we'll do, obviously, after Thursday and before the final, is have a bunch of office hours, the GSIs, myself, etc. So you should have plenty of opportunities to see the whole sort of course put together in 2 hours, and to see the emphasis of what the final is going to be. And I should say, I've said this a bunch of times, but I guess it bears repeating, that what we will be testing you on in this final really is going to be focused on the last third of the class. So the cosmology, large-scale structure, galaxies, etc. But we will be asking you questions that harken back to the other 2/3 of the class. The bias, again, is on cosmology, and some of the stuff you've been doing on your homework, in particular the one you just turned in, are the types of things we'll be asking you to do. Now, I should say, I know a lot of you found the last homework somewhat tedious in terms of the algebra. That's kind of on purpose. Obviously, we wouldn't give you tremendous amount of tedium on the final, but I wanted you to get a lot of practice going from the Friedmann equation to something else, right? So what are the terms that you can throw out given how the question is stated? What are the other things that you have to bring in? Giving you some practice in going from these very basic equations to something of great interest. I think it's sort of magical that you can figure out, for instance, what the Hubble constant is as a function of redshift just by starting off with the Friedmann equation. Right? Don't you think that's magic? Isn't that cool? So I wanted you to get that sense of course, there's a lot of algebra that you have to grind through, and you have to make a bunch of substitutions, but it's worth it, I think. Anyway, so the GSIs will hopefully summarize for you very well well, I know they will, what we'll be emphasizing on the final in that review. Yes? Will we give you some practice questions? Yes, we'll give you some practice questions. I would think we'll get you the practice questions certainly before the review. Whether we get you the answers by then, I don't know. But it'll be sort of around that time. We'll give you plenty of time with them. Any other questions? Okay. Oh, and obviously we'll start at 8:10 a.m. and I'll give you your 10-second warning. So it's a 2-hour and 50-minute exam, and bring in that one piece of paper that you've already put all your equations on from the first 2 midterms, and then add another half side of a piece of paper. Yes, one side of one sheet of paper you can add to, and on the other side put non-astronomy stuff on it. Okay. Or nothing. Yes.
You said that the final will be cumulative, but it will emphasize things in cosmos that we're doing now.
That's right. So we might ask you a question about black holes in a cosmological context or something, right? Or star formation as a function of redshift. I mean, we're going to try to tie back some of the concepts into cosmology, but in terms of like where most of the sort of hardcore physics that we'll be asking you to work out, it's going to be biased towards the last third, just because that's where most of the magic is. Any other questions? Okay. You'll have chances in the last week to ask me more questions about it. All right, so last time we did a lot. Oops, we started off with the fluid equation, and we came up with this nice formulation for how the scale factor changes for different constituents as a function of time based on this parameter W. And remember, W is a way in which we relate the pressure to the density, and mass density here, or you can rewrite this as an energy density just with a c squared. And we found that R goes like 3 times the quantity 1 plus W times the density of that constituent, and that is constant. Excuse me. 0 is a constant, but it's not the only constant. So that the implication of this for relativistic particles, so what you should be thinking about essentially photons, because W is 1/3, is that the mass energy density equivalent of these photons goes like R to the minus 4. And likewise, as we've seen in a couple lectures now, that the energy density or the mass density of matter itself goes like R to the minus 3. And that's true for baryons. That's true for dark matter. In a matter-dominated universe, something that you showed on your problem set just now, and there's a related thing that we showed in class of how omega matter changes as a function of redshift. We have a Hubble constant as a function of redshift, and this is for a matter-dominated universe. So that's where we ignore relativistic particles and we ignore lambda. And we found this equation here written on the board. And then the scale factor, as we saw in a matter-dominated universe, goes like T to the 2/3. Likewise, in a radiation-dominated universe, where if we're looking at the Friedmann equation, we basically ignore the matter contribution. And this makes sense not in sort of redshifts of around 1, but at redshifts around 10,000 and even higher, because of this right here. We know that even though the contribution of relativistic particles to the Friedmann equation now is very small, at some point in the past it was very large. So indeed, in the very early universe, the way in which the universe changed, that is, the way in which the scale factor evolved, depended largely upon the radiation and not so much upon the matter. And here, the temperature, capital T, went down like the square root of time. And we said that something like 1 second after the Big Bang, the temperature of the average photon, because there's a temperature equivalent to the photon energy, is something like 15 billion Kelvin. And the scale factor is going to go up like square root of T. We'll see in the last lecture that that's not actually the case at very, very early times. There was a period called the inflationary period, where the scale factor got very, very large exponentially with time. And right after that, we sort of coasted into this radiation-dominated phase. By looking at the values of this rho relativistic and rho matter today, and knowing what the critical density is today, that's something that we can measure because we can measure the Hubble constant, we can get values of omega relative and omega matter, and these are the numbers that your book presents to you. They're about what we think is correct today. These numbers are changing a little bit. I mean, one of the very exciting things, if you haven't caught on to this in your reading, is that these numbers are of great interest to us, and we are trying to understand exactly what their values are to the highest level of precision. And it's not easy to make these measurements, right? So one of the things that we're trying to do is hone in on the exact values of these things, and this is what's sort of called the error of precision cosmology. 15 years ago, these numbers were not nearly as well known as they are today. Well, this one was pretty well known, but that one not so much. And so even though your book gives you these numbers, in 15 years from now, when they wind up sort of doing the third edition of this book, or maybe a couple years from now, there'll be different numbers, right? And the age of the universe won't be 14 whatever that your book gives you. The current value is 13.75 gigayears. So these numbers are changing a little bit. It doesn't mean that the universe is sort of going through some crazy oscillatory phases or something. It just means that observational cosmologists are trying to arrive at these numbers in the most precise way we can. Anyway, so here's the numbers from your book, and these are the ones that we're going with. And that leads to a redshift when matter and radiation, or matter and relativistic particles, had an equal contribution to the Friedmann equation at something like a redshift of 3,270. Okay, so before that time, or at higher redshift, the universe was radiation dominated. And when we move beyond 3,270 to lower redshifts, that is when the universe was matter dominated. Okay, so any questions about that? What's clear, or what should be clear, is that as the scale factor keeps getting larger and larger, these values right here are going to be driven farther and farther down. So in a billion years from now, somebody who's doing cosmology would say that their omega m0 is a number which is smaller than this. And likewise, the temperature is going down in the universe, so this contribution is also going down. So if we again go back to the Friedmann equation, 1 over r times dr dt squared minus 8 pi g divided by 3 times the contributions from the relativistic particles and from matter minus 1/3 lambda c squared all times the quantity r squared minus kc squared. What's clear is that these terms are being driven to 0 as the expansion of the universe continues. Eventually, these numbers become so small that this, if this number is not 0, lambda is not 0, will actually wind up dominating how the universe evolves. Okay, so all of a sudden we've shifted from the functional dependence of this going like r to the minus 3, sorry, this going like r to the minus 4, and this going like r to the minus 3. All of a sudden we have sort of a new dependence within the Friedmann equation. So effectively, when we think about a lambda-dominated universe, we're sort of simplifying our lives and throwing out two of these terms that we've been spending most of our time on over the last few lectures. And if we assume that k is 0, which turns out to be a pretty good approximation observationally, we have a pretty easy way of looking at this equation and then solving for r as a function of time. Right? In a lambda-dominated universe, we throw this out. This on the right-hand side is equal to 0. We can multiply out the r squared, and we have dr dt squared. I'll put the 1/3 blah, blah, blah on the other side, 1/3 c squared lambda times r squared. Take the square root of this, and we just have dr divided by r by moving the r over to the other side, square root of 1/3 c squared lambda times dt. So if we want to now think about how the universe is going to evolve from here on out, because I will posit to you and we'll show in just a little bit that these terms are actually pretty comparable to each other around now, although this term is actually dominating the Friedmann equation. And as we move on, sort of in a billion years from now, this number will be even smaller. So what we want to know is how R is going to change with time going from now onward. Okay, so given that, we'll go from R equals 1, which is now, up to some other R. Limits of integration make sense here. T0, that is time now, up to some time a little bit later on. Okay, so what's the integral on the left-hand side? Log, and just any kind of log? Natural log, yeah. So it's not just any log. And this is square root of 1/3 lambda c squared t minus t0. So r of t is just going to be some exponent here, e to the square root of 1/3 lambda c squared t minus t0, plus some constant. Okay, so exponential. Well, what do you think the constant is?
Should it be in front of the
Yeah, it should be in front of the e. There's a c prime. Thank you. So how do we normalize this? What does the scale factor have to be today? 1. So if I put t equals t0, I get e to the 0, which is 1. So c prime is just constant. Equals 1. Okay, so what was I going to say about this? Oh, let's look at this equation right here, and let's put the r squared over to this side, and we get 1 over r squared dr dt squared is equal to 1/3 c squared lambda. What's this? Oh, yeah, thank you. What is this over here on the left-hand side? H squared. Is this H naught or is this H? It is H, but if I posit that this value of lambda, whatever this is constant, then it's H squared, but it's also H naught squared. Because we're assuming that this is a cosmological constant. So it's okay to do this. This is true for all time, right? That means I can put in for this something which is going to look like, this is going to look like H naught, right? So this is simply H naught t minus t naught. Okay? So, universe is running away. By the way, does the units work out? Yes, because the units of h and h naught are 1 over time, right? So why do we call this an accelerating universe? That should be also clear. What does it mean to accelerate? It means that we have a positive double dot. So r dot 1/3 lambda c squared r squared. If I take the derivative of this with respect to time, I get r double dot on the left-hand side. And again, this is all constant, so this is 1/3 lambda c squared 2r r dot. I can plug back in for r dot, and I get 1/9 lambda squared c to the 4th times 2 r, did I already do it all in? Yeah, r squared. So this is 2/9 lambda squared c to the 4th r cubed. Positive. Acceleration is positive. Universe is running away. Acceleration. We've been talking about ourselves living in a decelerating universe, right? Because we look at the Freeman equation, and what we see is that there's a counterbalance of what we were thinking of as the kinetic energy term and the potential energy term. But now when we get rid of that stuff, and we see how the universe is evolving without matter and without radiation, but just in the presence of this cosmological constant, we see that indeed r is growing exponentially, and there's an accelerating universe.
Can you explain how you got the first equation on the original simulation?
Right here?
Yeah.
Top here?
Yeah.
Didn't I just rewrote what I had before?
Then choose the r dot square.
Yeah, you're right. Thank you. All right, so let's take the square root and go like that. Is that okay?
That's fine.
Okay. And then, wait a second. What? Oh yeah, my notes are wrong. Okay, so let's redo this. It actually makes it a lot easier. All right, so everyone agree with this? All right, r double dot is equal to square root of 1/3 lambda c squared. Oh, then r dot. Yeah, oh, okay, good. All right, good, we're all right. So this means that, so we put the square root back in, we get 1/3 lambda c squared r. Okay. Happier? Okay, thank you. Thanks for noticing that. Still the right answer. It's not decelerating. If we had a minus sign there, I would be writing a Nature paper right now. All right. Man, my notes suck. I hate you, notes. All right. So let's again rewrite the Freeman equation. I know we keep on doing this, but you'll have to bear with me. And in some sense, this is its kind of most general form. It's going to be h squared minus the quantity omega matter plus omega relativistic plus omega lambda r squared is equal to minus kc squared. If we want to think about this, this is sometimes referred to as omega total. And if we think about how your book symbolizes omega total today, it's an omega naught, and this is omega total today. You sometimes see omega 0. So h naught squared, r naught squared, 1 minus omega 0. So doing this all, the context of today, is equal to minus kc squared, we can set this, because the kc squareds can be on both sides, we set this equal to this. And you can see from this r squared and this r naught squared, we're going to have a 1 plus z squared out there. And allows us now to solve for h in terms of h naught. And then what I'll do is just basically give you the final answer here. This is kind of, again, the most general thing without going through all the algebra. H of z is equal to h naught times 1 plus z, all times the quantity omega matter today times 1 plus z plus omega relativistic today, 1 plus z squared plus omega lambda today divided by 1 plus z squared plus 1 minus omega 0 all to the 1/2 power. What I haven't told you is what is omega lambda. Omega lambda is just going to be something we'll define. First of all, start off with rho lambda will be defined to be lambda c squared divided by 8 pi over g. That actually uses lambda and winds us basically allows us to put this term on sort of equal footing with these terms right here. This is obviously a constant. So this also is going to equal rho lambda 0. And then, just like we define the other terms, we'll have omega is equal to rho lambda divided by the critical density at whatever time that is. So this is pretty interesting. Again, this means that if I can measure the Hubble constant, did I get the term wrong? No. Yes, Stuart.
How do we keep treating lambda as a constant? Doesn't it change over time?
This is some value that is some sort of has some sort of physical meaning that no one has figured out yet. This is like saying the fine structure constant or the mass of the electron or the strength of the Coulomb force. It's just some other term that's in nature, and we have no idea why it's not 0. And we will talk about just briefly in the last lecture why this number isn't exactly 0 when because it has to do with sort of an energy. We would think that this is somehow related to the vacuum energy. So the vacuum has some sort of energy associated with it, and we can come up with what that is. And you can just basically manipulate Planck's constants and Planck length and all that and get a Planck energy. And you find out that that number is really small, but it's not 0. The fact that this number is slightly different than 0 is really disturbing. But the way to think about it is it's a physical constant that no one ever taught you in high school physics. This is to say that this is sort of I won't say it's the most general, but it's the most basic formulation of the universe with a cosmological constant. You're indeed right to say that this could have some functional dependence on time, or it could have some value when the universe is above some temperature, and then all of a sudden it switches to some other value, right? We don't know. We're just assuming that this is constant because all the data so far are telling us that it is constant. That's what we'll talk about basically now. So thank you. I'll send you your $5. Any questions about this formulation, however? This is how we understand Hubble's constant as a function of time. And we'll sort of flesh out a little bit how it's going to wind up changing as we crank up and down these different values. This is a very small term right now. So if we're thinking about the universe and things that we could observe, like what we're going to try to figure out is how this formulation can be observable in something that we can actually get our hands on, right? And the answer is supernovae and other things. One of the first answers was supernovae. And you've seen this plot before, where we have distance and apparent recession velocity. No matter what universe we live in, everyone's measuring the Hubble constant. You could convince yourself that if I set z equal to a very small number, h of z is going to be very close to h naught, right? So everybody, regardless of what these different terms are going to wind up measuring the same Hubble constant. And you saw that if the universe had no matter in it, it would basically be the same Hubble constant for all time. If it had some matter in it, then the universe would be decelerating for all time, right? Which means that in the past, that slope was larger. In the mid-1990s, people started looking, I'll turn off the lights for a second, started looking at distant supernovae and started recognizing something interesting. This is a sort of wide picture at the top from Hubble Space Telescope and a very deep image of a very distant supernova around redshift of 1. And what they did is they took two different images from this very deep image from Hubble taken at different times, and they basically subtracted the two off. And you see that there's some residuals in the subtraction image from this very bright galaxy, so it didn't subtract perfectly. But even though your eye can't see one little point source here, it's pretty obvious that there's a new source, right? So between an image taken in 1997 and 1995, there's this new source. So this is how people found and do find distant supernovae. And here's a couple of different images of different very distant supernovae that people have observed. So here's sort of the before image, and there's the after image or the during image. And again, here, this is a very complicated galaxy. It's very hard to see that there's a new supernova, but deeply embedded in there, there is indeed a supernova, right? And the arrows are telling us where to look here. So what does it mean to observe supernovae and to infer that the universe is accelerating? Well, that's a bunch of different conceptual and observational leaps. But fundamentally, if we go back to this plot, by measuring the Hubble constant, which is essentially the slope as a function of time, we're getting at the measurement of distance, right, as a function of redshift. Or put it another way, if I can measure the distance to a source and I can measure its redshift from us, then I'm getting some sort of measurement of the Hubble constant as a function of redshift, right? And in fact, it's not the Hubble constant as a function of redshift that you measure in an instantaneous sense. It's sort of the integrated value of the Hubble constant all the way back. It's some measurement of some sort of concept of a distance, which we'll talk about now. Anyway, what's observed is that. So it looks like as we go farther and farther back in time, the expansion was slower in the past. And if you turn that around, it means that the universe is today accelerating. Now, there's no way to get the universe to accelerate if we just appeal to the Friedmann equation without dark energy. We throw this out, the things you've been working on your last homework and you saw in the last few lectures, these terms wind up dominating, and all they know how to do is slow up the universe. There is, in this concept of the fluid equation, there is this concept of a negative pressure, and it's that negative pressure being exerted by this dark energy constant that is causing us to currently accelerate. So what I'll do now is we'll work out how we can relate observations to an inference of these quantities here. But just to sort of cut to the chase, omega matter, as you know, is something like 0.27. Omega lambda is something that we infer, and that looks like it's about 0.73. And omega relativistic is, what did I say, 8 times 10 to the minus 5 today. What do you notice about this if I call all this stuff omega total? It means that omega total today, which is sometimes referred to as just omega naught, is very, very close to 1. This is why I've been telling you that k is about equal to 0. If I put this equal to 1, then the left-hand side has to equal 0. We know that this is a positive definite number. That's some number, which we call 1, so it means that k has to equal 0. In fact, the current value is that it's 1.02 plus or minus 0.02. So within 1 sigma, as we say, because this is an uncertainty that's related to the measurement errors, within 1 sigma, this total value is consistent with 1. And as I said last time, billions of your tax dollars will be spent, actually billions of euros will be spent in trying to understand if this is exactly 1 or something slightly different from 1. The new mission that Europe is going to be launching, by the way, to actually look at supernovae and look at a couple of other ways of getting at these cosmological parameters is called Euclid, which I'll go on record, because I'm on tape here, as saying is one of the stupidest names for a mission, because it's presupposing the answer, right? That Euclid was right and k equals 0. You'd want to call it like Euclid plus or minus epsilon or something, and I think that would be much more motivating. In section, by the way, and this is something that I do want you to make sure that you work out. If you can't go to section, look at the answer key from the sections after those are posted. There is a time, just like we had a matter, I think I've gotten rid of it, we had a matter radiation equality, which was happening Z matter equals radiation, and that was, what did I say, 3,270. There's also a redshift when matter and the lambda term in the Friedmann equation are also of about the same value, and that turns out to be about 0.7. Oh, sorry, that's 0.3. R is equal to 0.7. So you'll go through that, and you need to know this quantity right here to get that answer. So, why did I put that in there? So this means that around redshift of 0.3, the universe went from being matter-dominated to being lambda-dominated. And so the Earth, which was born about 5 billion years ago, was born at a time in the universe when the universal expansion was being dominated by matter. And now we're living in a time when the universal expansion is being dominated by this lambda term. So if we try to just sort of tie it all together before I move on to how we make measurements of distance and how we do observational cosmology and astronomy, here's density on the y-axis, and here's R. The omega term, the lambda term is going to be some sort of constant with R. That's what we posited by saying that this value of lambda is indeed constant. We know today that the contribution from matter is very small, relative, well, it's actually smaller than the contribution from this term here. And we know that this went like r to the minus 3 in the past. This is matter. Also, radiation is way down here. We'll do this in log space to make our life easier. And this had a different functional dependence, r to the minus 4th, radiation. So here we are today. This is r equals 1. And this is the redshift of when matter and lambda were the same. And this is the redshift when matter and radiation were the same, or contributed the same. So it's a bit complicated, but what you see here is that we have our radiation-dominated universe, or matter-dominated universe. And only just recently in the history of the universe have we become lambda-dominated. Again, this is something that we worked out last time. This is something that you'll work out in section, okay? Okay, so how do we measure h of z Because clearly, if I make a measurement of h of z, and I know h naught today, because there's different sets of measurements I can make, I can start getting a handle on these different quantities here by basically fitting the data. Well, it turns out that h of z is related to our concept of distance. And the way that we make measurements of distance in astronomy, if we can't do this in a parallax way, is fundamentally about standard candles, right? And we've talked about supernovae already as standard candles, but the assumption here is that they have some peak luminosity that's all the same or calibratable, and we're going to measure their flux, and by measuring their flux and inferring that they're all the same or calibratable, we're going to wind up getting a measurement of distance. How do we know distance? Well, we say that flux is luminosity divided by 4 pi d squared. This is just the 1 over r squared law. Units of flux are what? Watts per meter squared. Units of luminosity, watts. Okay? So if we can infer what this is for supernovae, for instance, and this is something we can measure, then we can get some sort of proxy for distance. What is d? Well, it's got to be related to the instantaneous distance between us and the source, right? This is something we call d proper. So this is if I just sort of could put down a bunch of ruler sticks right now and measure it without any expansion of the universe, the distance between me and that source. However, the light has taken sort of a different path. Well, it's taken a radial path to get to us, but something's happened to the light along the way. What's happened to the light as it's been traveling through this expanding universe? It's been redshifted. So it's effectively lost energy. What else? Think about this in the context of flux. What is flux if I'm measuring individual photons arriving from a source? How many photons you count per unit time? So if I'm measuring a source and it's emitting, say, 1 photon every second towards me in its own frame, and it's moving away from me, or effectively moving away from me, then am I measuring the same amount of, or the same arrival rate of those photons as what's left? No. Is it gone up or down? Gone down. There's something called time dilation. And we've seen this a bunch of times, but in the context of GR, in the context of special relativity, now we have time dilation, which is cosmological. Okay, these two effects contribute like 1 plus z and 1 plus z. So that the flux that we observe, because the flux is units of energy per unit time, the energy's gone down, the rate has gone down, and so this whole thing is down by a factor of 1 plus z relative to what you'd naively expect if you just measure the distance between us and the source. Purely cosmological. So what we do is we define what's called the luminosity distance such that this equation is correct. And by definition, the flux will be F equals L divided by 4 pi dl squared. And this is L divided by 4 pi 1 plus z squared times d proper squared. So clearly, the luminosity distance is just 1 plus z times d proper. So here's some supernovae, different types of supernovae. The one at the top, type 1a supernovae, is a spectrum as would be observed in the optical wave bands at a redshift of z equals 0. So that's around us today. And these, ooh, hello. That's a redshift that, I think my computer's dying. That's a redshift that we would be able to use to standardize our candle because we'd have a measurement of distance to that source. Don't really pay attention to the other supernovae down there. Recognize that there are some features within that 1a supernova that we could use. And now let's put that supernova, all those supernovae at a different redshift of 0.1. And what's going to happen, we're going to observe them to shift to the right on this curve right here, on this plot right here. So they would wind up, these different features would be observed at slightly longer wavelengths. However, if we know the redshift, we can blue shift what we observe back to the rest frame. So what you're going to see is that I'm going to push this thing out to farther and farther redshifts. These are going to become noisier and noisier and noisier. But if we know what the redshift is, we can see what this would look like in the rest frame. However, if I'm observing in a fixed sort of window of observation, say between 3,000 and 8,000 angstroms, and the spectrum is shifting farther and farther out of my bandpass, effectively I'm losing information about the reddest part of that spectrum. So what you'll see also is that this hash thing comes in. You can see even a redshift of 0.5, and this is some sort of simulation of what these supernovae would look like for, say, a 4-meter telescope with an hour or so of integration time. You can still see that there are some features in that spectrum, even though it's gotten noisier, that I could tell, right? So I could say that I'm indeed looking at a 1A supernova. So the point here is that I can make a measurement of a supernova, a bunch of different supernovae at different redshifts. I can make a measurement of their flux, right? And I can also notice that there's time dilation. It turns out that when you look at a type 1a supernova spectrum, you can the features are changing as a function of time. And the time since the explosion is basically encoded in what you see in the spectrum. So in addition to being able to just take a spectrum and say, that is, 41 days after that explosion, you can also see how the whole light curve is evolving as a function of time. And what people have been able to do, there was a graduate student in our department who graduated a few years back, did this as one of the chapters of his thesis. He observed the light curve as a function of time, and then he time dilated it, or untime dilated it, back to the typical supernova that we see at redshift of 0. And he also was able to, from the spectrum itself, figure out the time that the supernova thought it had been since it exploded, based on the spectrum. And those two things wound up agreeing. So it's essentially proof, in some ways, of cosmological time dilation. All right, so before we move on, we have to now figure out what is the proper distance to a source. Any questions before I go on? No? Okay. So what is d proper? Well, as I hinted at, d proper is some sort of instantaneous measure of the distance between me and a distant source. So to make such measurements, because you're all so hip to the metric, you know that we have to take our metric and we have to figure out that d proper is what we've in the past called this script L, and this is just the square root, the integral of the square root of minus ds squared with dt equal to 0. That is, it's the instantaneous distance. So this is from the Robertson-Walker metric, and if you go back in your notes and you set dt equal to 0, and we think about motion in a radial sense, then we throw all the other spatial terms out, and we get ds squared is equal to minus r of t squared dr varp divided by 1 minus k r varp squared. Remember the Friedmann-Walker? I don't want to write it all down again, but everyone okay with this? No problems? Okay. So that means that d proper is the integral of r of t dr varp 1 minus k r varp squared. And this is going from some distant galaxy to us in a coordinate distance sense, right? So this is the galaxy where the supernova went off. Supernova. Its coordinate distance and our coordinate distance. There is, thank you. I'm not being very good today. Yes, and it's in my notes, so I can't blame my notes. Okay. So we're integrating over some sort of coordinate distance. This is a little bit of a trick, but what is, if I want to know this value today, how do I deal with this capital R of t? Turns out R of t doesn't depend upon this coordinate distance, right? I'm just going to make an integral from me to some other galaxy just using the coordinates, the co-moving coordinates. I don't care what the overall scale factor is today. So this is constant with respect to this R varp. That's a little bit strange, but think about it. Okay, stop thinking about it. So this is R t of today. Integral over the galaxy, us, dr varp square root of 1 minus k r varp squared. Yes? Remember that we think of R as this dimensionless scale factor, and that's the thing that's changing. But the distance between me and a distant galaxy or me and a distant galaxy cluster is actually fixed in co-moving coordinates. We can draw out this coordinate system, and here's you, and here's some galaxy. R varp is just changing, by some amount from us to that galaxy. And a galaxy that's nearby will have r varp be, or dr varp be smaller if I integrate over all the d varp. So if I have galaxy 1 and galaxy 2, this quantity will be smaller than that quantity. So if I'm just doing integrals over this coordinate space, it doesn't matter what the physical distance is between each one of these different grid points. That's given by this r of t. So I can do this integral without respect to that. Yeah, we would put, so we want to know the proper distance between us today and a distant galaxy. Is that all right?
Yeah, it's like, it's sort of weird to think about, looking at a distant galaxy and looking at two different times.
But we want to know instantaneously, and we need to know the scale factor today for that. Let me carry through the rest of this, and hopefully it'll make sense. So for photons, ds squared is equal to 0. So if I want to convert this into something where I'm now going to figure out the relationship with time, for photons, ds squared is 0. Because, of course, the photons are not sort of traveling instantaneously from us, the galaxy. They have to travel through this expanding space. So that means that c dt is equal to r of t drw divided by square root of 1 minus krw squared, because we're going to see how these photons travel through that space. So we can plug in, put the r of t down over here, and we can plug in for this quantity on the right-hand side into this equation. So this is going to be r of today from the galaxy or the supernova to us, c dt divided by r of t. And now, since I'm integrating with respect to time, and the scale factor is changing with time, your intuition's right that I have to pay attention to that, and I can't just pull this out now. So here, one of the little clever tricks is to say that dt is equal to dr divided by dr dt, and this is just dr divided by r dot. So I'll put that back in there. Let me go over here. So d proper is equal to r today. Integral, let's actually pay attention to the integral now, because we're doing this with respect to time. This is the time emitted, and this is time observed. So c, what did I say, dr, r dot r. Everyone okay with that? Now I have to change, if I want to now do this in redshift space, we'll say that r is like 1 over 1 plus z. So dr is equal to negative 1 over 1 plus z dz. So I can make these substitutions right here. And I get r today, z, because that's going to be related to the time that it's emitted, the redshift of that galaxy or that supernova, to 0 minus r squared c dz r dot. If I want to flip the limits of integration, I can get rid of the minus sign, and I get r today, now going from 0 to z, and this just simplifies to c dz divided by h of z. So remember, h is just r dot divided by r. R of today is what? So this is just c integral from 0 to z of dz divided by h of z. It's a lot of work just to sort of get back our intuition that if I had to think about sort of a proper distance and all I had was light and all I had was expansion of the universe as a function of redshift, you can imagine that dimensionally it basically has to work out this way. Kilometers per second per megaparsec, right? If I put that on the in the denominator, then the kilometers per second are going to wind up canceling out, and we're going to get some distance in units of megaparsecs. All right, so here's how all this ties together. First of all, any questions about the derivation? Everyone's okay with this? Here's how it all ties together. Here's h of z. Here's some integral over h of z. And here's some super nastiness of h of z. As a function of stuff I'd really like to know, like I could put in h naught if I had that, right? And I'd love to know these quantities right here. This means that if I have a way of making a measurement of d proper as a function now of redshift z, it means I can map out effectively how this integral changes with z. which is a way of me getting constraints on all of this stuff in here. So observational cosmology, as we understand it, is trying to figure out what d proper is as a function of redshift. And we can do this in a luminosity sense, right? If we figure out what the true luminosity of a standard candle is, or standardizable candle, measure its flux, get its redshift, get d proper at that redshift. We now know what the value of this integral is. We can get those constraints in those terms. Now do it for another supernova. Nobel Prize. Right? Just keep on turning the crank. So indeed, this is what people have been trying to do for a long time, and they've been able to actually carry this out. By the way, if we just take out the H naught, let me see where I'm going to rewrite this. Right, on the left-hand side of the board, you see that h of z goes like something like h naught. If I put all this stuff back in, I can rewrite d proper, and it's clearly going to go like c divided by h naught times some sort of nasty integral. So if I change h naught a little bit, I'm changing the proper distance by a lot, right, or by 1 over that. In the low z limit, that is not at super high redshift, the luminosity distance, if you then basically carry through this integral, is like cz divided by h naught, 1 plus z divided by 2, 1 minus 1/2 omega matter 0 plus omega lambda 0. That's just, assume that z is less than, say, 1. There's some things to see here. Of course, luminosity distance is going like c divided by h naught. It sort of has to do that dimensionally. At very low redshifts, you might throw out this term, and it sort of gives back our conception of what it means to talk about in the context of an expanding universe. What is CZ? That's just the apparent redshift, and CZ is just h times d, getting back to Hubble law, h naught. But it's a little bit more complicated than that. Something that's important to recognize is that if I crank up the value of omega matter, what happens to dl, the luminosity distance? It decreases. So we add more of this term here, we get more negative, and then this term gets smaller than we add on less. But the converse is true. If we wind up increasing omega lambda, then we wind up adding more on this term right here, and dl gets bigger. Now let's think about it before we actually start looking at some data. What does that mean for an observation of a supernova? Let's say I didn't have omega lambda, right? Omega lambda 0. We're living in a sort of open universe, and all there is matter. Forget about even the relativistic particles. First of all, wait, before I do that, why is omega relativistic not part of this simplification? Because it's tiny, right? It's in there, right? If you're going to do this fully out, you'd have to care about it. But at redshifts less than 1, we know that the universe is not being driven by the radiation. Okay, so that's one thing. Forget about omega lambda now for a second. For a given fixed amount of omega matter, I'm going to have some luminosity distance. Now let me add some number right here. What just happened to the luminosity distance? It went up. So did the supernova just get brighter or fainter? It got fainter. In a universe that has dark energy, or cosmological constant, supernovae, or any standard candle, are fainter than they ought to be at a fixed redshift for a fixed amount of omega matter. Okay? So if I observe a supernova and all I think that there is in the universe is omega matter, right? All I think there is dark matter and baryons and all that stuff, and that's something that I think I know how to make a measurement of locally by looking at clusters of galaxies. And I come up with a number of like 0.3, and then I look at these supernovae. Those supernovae are fainter than they ought to be. Let's see now the functional dependence on the luminosity distance as a function of these two parameters. Hold on one sec. Given the constraint that omega total is about equal to omega matter plus omega lambda today. And this is about 1. So given that constraint, if I crank up omega matter, then I wind up having supernova be brighter. If I crank up omega lambda, then I have supernova wind up being fainter. We're starting off with omega matter today of 0, but we're subjecting ourselves to the constraint that the total omega naught is equal to 1. And it's exactly what we just said. We're going to go back up to the top. We're going to assume, fix yourself at some fixed redshift, say 1. And now omega matter is basically 0 when this thing hits the top. So we have only omega lambda. And when you have only omega lambda, the luminosity distance at a fixed redshift is larger. So supernovae are fainter. There's nothing that says that the cosmological constant can't be a negative value, right? So it could actually have the total be, or the total be 1, but have omega matter be 1.5. So omega lambda be negative 0.5. There's nothing wrong with that. And so what it should be clear here is that if I make measurements of supernovae as a function of redshift, what I'm really doing is mapping out this proper distance, which is me making a constraint on these different terms. What do you notice about low redshifts, less than 0.1? For all the different cosmologies, all these two different cosmological parameters that I'm dialing in, I get exactly the same slope. And that slope is the Hubble constant. So no matter what I do in the local universe, forget about making measurements of cosmology. It's really hard. It gets a lot easier when you make measurements of things that are much further away, right? Because that's where things are much more manifest in this wiggling of this luminosity curve. It's a little bit more subtle than that for realistic cosmologies. Here is now redshift in a log sense, so 0.01, you're really nearby, 0.1 and 1. And here are 3 different cosmologies which aren't nutty. This, 15 years ago is the universe that we thought we lived in. 25 years ago, this is the universe we thought we lived in. This is the universe that we think we live in today. And what you see is now not luminosity distance, but what is that? Distance modulus. Little m minus big M. Big M is the absolute magnitude, for instance, of a supernova. Little m is the apparent magnitude. And this is just this proxy for distance 5 times the log of the distance divided by 10 parsecs. So that distance now is a luminosity distance. It's not just any old distance, it's dl. And look at the differences at redshift of 1 between these two different cosmologies. It's not huge, right? And in fact, you might even argue that it's somewhat subtle. But it can differ by sort of 1 magnitude. So a supernova in this universe relative to this universe is going to be different by, in this case, maybe 0.2 magnitudes. So you're looking for a 20% difference for a supernova that's incredibly faint from what you think it should be. This is why this is hard. This is why it took a long time for people to figure this out. This is from the Supernova Cosmology Project that's based out of LBL. And you can see now apparent brightness. So this is basically not luminosity distance, but effective apparent magnitude. And you can see these different plots of the location of different supernovae on this curve. And actually, this is an average of many, many supernovae. And again, you see that at small redshift, doesn't matter what cosmology you live in. The only thing that matters is h naught, right? But that sort of sets the whole scale for the thing. And then you see where the other data live. So supernovae, as you go farther and farther away, look like they're actually fainter than they ought to be if there wasn't any cosmological constant term. So this is another way to visualize this. I won't go into the details here, but there are different types of universes you can imagine, and we now believe we're in this accelerating universe because of the supernova data. Harkening back to some of the stuff we did in the first third of the class, what other effects can there be in the universe that make things that are farther away appear to be fainter than they ought to be? Extinction. So how do we know this is not dust? How do we know there's not intergalactic dust? That's just a little bit of that stuff. And the light travels so far, it goes through all of this dust, it just gets highly extinguished. Yeah. Yep, we could do this at very long wavelengths that basically don't care about dust. But what would, if it was normal dust, like the stuff that we see in galaxies and in our atmosphere, what would be another effect other than just dimming? Reddening. Well, we see reddening because we have cosmological redshift. So we do see reddening.
Would you be able to detect it in our local universe?
In what sense?
You just showed that the effects of supernova are more prominent the further you get from us. But if there was, and there's not much difference if they're close by, but if there's dust, you'd be able to see the difference.
Well, how would you notice that distance? You're right, but how would we notice it observationally? How do we know that there's not reddening in supernovae? Dust reddening. No spike?
Isn't there a spike where the average size of dust particles are?
Oh yeah, so there's definitely a 21 centimeter or 2175 angstrom. 21 centimeter. I don't know where that's coming from. 2175 angstrom bump, which is probably related to dust grain size. It's hard to see because it's in the ultraviolet. Yeah.
Cosmological redshift will move all the spectral lines for extinction.
What will extinction do?
It'll just preferentially get rid of higher frequency.
Yes, exactly. So reddening in this sense is not that we just take every spectrum and we redshift it and we multiply basically every observed wavelength by 1 plus z. Instead, you take the overall spectrum and instead of it looking like this, it looks like it's bent over, right? And so what we see, or what we don't see, as we observe these supernovae at farther and farther away, is we don't see any evidence for this sort of reddening. Now, that's okay, but one way to wiggle out of this, as you know, is that you just have different dust, right? If dust is in the form of bowling balls or dust bunnies, sorry for those that didn't like your midterm, what happens, right? There's not now reddening. It's just basically extinction. So this is what's called gray dust. So dust bunnies equals gray dust. Gray dust is something that doesn't cause a color change, but only causes an extinction. So for a long time, people were very worried that people were claiming, oh, we've got evidence for an accelerating universe, essentially just from these supernovae. And then other people who were skeptical said, well, but you have gray dust, right? Gray dust could actually let you wiggle out of that problem. Because you can construct a universe such that you wind up getting just the right amount of gray dust to make things farther and farther away appear fainter and fainter than they ought to be. However, what should happen if I go beyond redshift of 1, redshift 2, redshift 3? It should just get fainter and fainter and fainter and fainter. However, because we now sort of after redshift of 4, we start going back into the universe when the universe was actually matter dominated. By the time we get to redshift of, say, 1 and 1.5, there's almost no contribution from lambda. So the curves here actually wind up sort of turning around. And what people have been able to see is that the luminosity distance indeed gets turned around redshift of 1. It starts turning back over and down. I won't expect you to understand this because it's a complicated plot. But the point is that people have been able to figure out this is even more complicated, have been able to figure out how it's not dust that gives us that turnover. So indeed, if you go from redshift of 0.5 to 1 to 1.5, here's the data right here, and you see it turning over here. If it was dust, it would just get fainter and fainter and fainter. So observationally, unless these supernovae are being really mean to us and telling us something that doesn't actually exist, that it's actually some sort of evolution in how supernovae change their effective brightness as a function of cosmic time, which isn't crazy, for all intents and purposes, it looks like gray dust is ruled out and is indeed something which just falls along this curve. Okay, so we have constraints from supernovae. M minus big M is equal to 43.124 plus 5 log base 10 of z plus 1.086, 1 minus 1/2 omega matter 0 plus omega lambda 0 times the quantity z. And remember, m minus capital M is 5 log base 10 of the luminosity distance divided by 10 parsecs. One subtle thing here is that we're talking about bolometric magnitudes and not sort of magnitudes in a certain waveband, but you don't have to recognize it. So all I have to do is make a measurement of a bunch of supernovae whose capital M I think I know, and then I have constraints on these guys right here. And the constraints that come out of supernovae look like this. Omega matter on the x-axis, omega lambda on the y-axis. 1, 2, 1, 2. Omega total of 1 is this curve right here. And what supernovae wind up giving us essentially constraints that look like this. So the best fit position is indeed on this curve right here. And these are sort of error contours. So this might be a 3 sigma error contour and a 2 sigma error contour. So the universe could basically be anywhere in here if we assume that indeed supernovae are standardizable candles. But the best fit number is here. And what you notice that omega matter is about 0.27. And omega lambda is 0.73. The thing, again, to remember is that in a lambda-dominated universe, supernovae are fainter than expected. All right, so what we'll pick up with on next Tuesday is trying to get at this proper distance, not through standard candles, but through standard rulers. And there we would make use of the cosmic background radiation. So what we'll have to do is talk about the origin of the cosmic background radiation and what sort of features we might expect to see within that cosmic background radiation.